Right, in this video I'm just going to finish the review of angular momentum, the concept that we left off studying in class. So in question 1, here we're on page 22 in the rotational motion notes. So question 1 asks us to explain what is meant by rotational inertia and write an equation. Well, rotational inertia we've talked about as being how hard it is to change an object's angular velocity, and we can write an equation for that. So rotational inertia is how hard it is to change an object's angular velocity. And we have sort of two relevant equations. So I is equal to mr squared, and I is equal to tau over alpha. So this is the equation that we use to calculate the rotational inertia of an object, where r is the effective radius of the object. And this second equation explains how the rotational inertia relates to the angular acceleration of an object. Okay, explain what is meant by angular momentum and write an equation. So we can understand angular momentum as a kind of how hard it is to stop something that is spinning. How hard it is to stop something that is spinning. It's described by the equation L is equal to I times omega. Explain what is meant by conservation of angular momentum. So here we say that unless acted on by an external torque, the total angular momentum of a system remains constant. And remains constant is the same thing as being conserved. So that's what this word conservation means. All right, and then a little application here. So a spinning bike wheel slows down. So if you get your bike out and you set one of the wheels spinning, it will eventually slow down and stop. And it asks, why does this not break the law of conservation of angular momentum? And that is because in this case, there is an external torque. And that's the torque that's provided by friction in the axle. Or hub of the wheel. So at the center of the wheel there'll be a hub where it's connected, and there'll be some friction there that'll produce a torque that opposes the motion. Okay, so now we're looking at a couple of examples here. So one commonly used example that we've talked a little bit about in class is that people that are trying to do flips use the conservation of angular momentum to get the rotation right. So a diver tries to make as many turns as possible. So she tries to maximize her angular velocity. That's so she can complete as many rotations as possible before she hits the water. Once she's spinning, she tucks, and this means that she brings her arms and legs in. This reduces her rotational inertia and increases our angular velocity. We can say as angular momentum is conserved. All right. Another interesting application is helicopters. So a helicopter has a spinning rotor on the top, and they often have a tail rotor at the back here as well. So what happens when the rotor starts spinning, it'll gain momentum, and if we're looking from above, it's in the clockwise direction here, so this way. To conserve angular momentum then, so if it was in the air and this was happening, the body would have to start spinning in the opposite direction. So that the body of the helicopter would spin in that direction, which would be very awkward for the people sitting inside. And to stop this anti-clockwise rotation of the body, we need an external torque about the center of the helicopter. And that torque is provided by this tail rotor, which is going to push the body in the opposite direction. So the tail rotor here is going to push the body, in the opposite direction to the direction that it's trying to spin. So it's going to push the body this way to prevent it from rotating anti-clockwise. Okay, so that's an interesting application. We often see in Hollywood action films that they shoot out this tail rotor and then the helicopter goes into a spin before it crashes. All right, so the tail rotor, it asks here at the end, which way does the tail rotor push in the above diagram? Well, the tail rotor has to stop this rotation this way. So it's going to have to push that way, so downwards. Kind of to make the body well, we can say not to make the body, but to push the body in the clockwise direction. In other words, to prevent the anti-clockwise spin. Okay, so this is an interesting question as well. This one, it says extension, but it's really an application of the same thing. So space stations, in order to turn them, they'll have a fixed electric motor with a heavy wheel. And we can say that by making the wheel spin inside the space station, the station will spin in the opposite direction to conserve angular momentum. So in other words, if you want to change the orientation of your space station or your satellite, you'll have a set of wheels inside that you are connected to an electric motor. When you make them spin, the space station can be made to spin in the opposite direction, and using that we can orient the space station. Okay, so here are some problems to solve. So we have a 250 gram turntable with a 15 centimeter radius. So that's 0.15 meters, and this is 0.25 kilograms. And it spins once every 2.5 seconds. So here, omega is equal to, if it spins once, that's 2 pi over 2.5. An identical turntable is dropped onto it. Okay, so we're going to double the rotational inertia. So what quantity is conserved? We can say angular momentum, if we ignore friction. Okay, the new angular velocity, well, I has doubled. So omega must have, and omega initial was 2 pi over 2.5, which is 2 times pi divided by 2.5 is 2.5. Equals 2.5, and omega f is equal to half of omega I, which is equal to 1.26. Radians per second. Repeat B for a drop turntable with the same mass but half the radius. So if we have the radius, that's gonna, because I is equal to half mr squared, if we half the radius, then I is going to decrease by a factor of 4. So I is equal to let's just work out exactly what it is. So I is equal to 0.25 times the radius was 15 centimeter before. It is now 7.5 centimeters, so 0.075 squared. And because it's a disk, it's half, so we'll divide that by 2. So that's equal to 0.25 times 0.075 squared divided by 2. So that's 7.0 times 10 to the minus 4, or 0.00070. 3125, and that's kilogram meters squared. And so omega I, so this is, so I final is equal to, well, this is the thing that was dropped. And we should really work out what the total initial angular momentum was. So Li, which we didn't do here because we didn't need to, but Li is going to be, initially what's spinning is just this turntable here at that speed. It is 0.25 times 0.15 squared over 2 times 2 pi over 2.5. That's the initial. Oh, let me just make that look more like an initial. Which is 0.25 times 0.15 squared divided by 2 times 2 pi divided by 2.5 is 0.0033534. And that is kilogram meters squared per second. And that must be equal to LF, which is equal to IF omega F, which is equal to, and now we want the sum of the two rotational inertias. So that's 0.25 times 0.15 squared over 2 plus 0.000703125 times omega f. So I'll just go up here and finish it off. So omega f is going to be equal to the total angular momentum divided by this big rotational inertia thing. So that's 0.003534 over whatever that is. So let's work that out. So what was that? 0.25 times 0.15 squared divided by 2 plus 0.00070, what was it? 703125. So that's 0.0035. So you can see it's 0.0035 divided by 0.0035. So that's about 1 radians per second. Okay, so we ended up having to do a lot of work for that question, and that's because we took some shortcuts for this one and we hadn't worked out what the rotational inertia was. Okay, the next one says, consider a merry-go-round. Estimate the rotational inertia of the merry-go-round. Okay, so now the question is, do we estimate that this is like a disk or like a ring? And I'm going to say that most of the mass is in the platform bit here, which is more like a disk. And so I is equal to a half mr squared, which is, the mass is 1,000 kilograms, so half times 1,000 times 3 squared, which is 0.5 times 1,000 times 3 squared is 4,500 kilogram meters squared. Okay, so that's the rotational inertia. Discuss your assumptions. Well, we assumed that the merry-go-round is like a disk, i.e. mass evenly distributed. Now, clearly that's not really true, but maybe if we think about all the horses and things, and if we think about the hub, and we think about the roof, and take all that together, then maybe on average it's more like a disk than it is like a ring. Okay, we then have a 100 kilogram woman who runs at 10 meters per second tangential to the rim of the stationary merry-go-round. What's her angular momentum about the center of the merry-go-round? Well, she's like a particle, and when she runs past the merry-go-round, when she's at the edge of the merry-go-round, her angular momentum is going to be like that of a particle. And we derive the equation, which is also given to you on your formula sheet for the angular momentum. It's just L is equal to mvr. And that will give us, her mass is 100 kilograms. Her speed is 10 meters per second. And she's running tangential to the rim of the merry-go-round. The merry-go-round's radius is 3. So it's times 3. So 100 times 10 is 1,000, times 3 is 3,000. Kilogram meters squared per second. Okay. Assuming she gives all of her angular momentum to the merry-go-round, calculate the angular velocity of the merry-go-round after she lands on it. Okay, so here we will assume that her rotational inertia is very small, and so I is just going to be this, and the angular momentum is going to be this before and after. And so all we need to do then is say that L is equal to I omega. So omega is equal to L over I, which is 3,000 over, and it was it 4,500? Yep, 4,500. And that's 0.67 radians per second. Okay, is it true that she gives all of her angular momentum to the merry-go-round? And it's not, because she, when she's on the merry-go-round, will still have some angular momentum. She still has some angular momentum. Because she's going to be spinning along with the merry-go-round. So calculate the actual angular velocity. This is an extension question. So all we need to do really is go, instead of using just the rotational inertia of the merry-go-round, we'll do the rotational inertia of the merry-go-round plus her. So I total will be 4,500 plus her rotational inertia. And she was 100 kilograms and all of her mass was 3 meters away. So that's 100 times 3 squared, which is 100 times 9, which is 900. So the total is 5,400 kilogram meters squared, not 4,500. And so omega will be equal to 3,000 over 5,400, which is 0.56. Radians per second. Explain what happens to the angular velocity if she then walks towards the center. So mass will be closer to axis of rotation. This means that I will reduce. Oh, I will get smaller, sounds better. If I gets smaller and angular momentum is conserved, L is conserved. So as L equals I omega, if I decreases, omega increases. Okay, so that's very similar to the situation that we had with the pulling in the weights while sitting on the spinning office chair. Okay, so those are the kind of practice questions and some applications of angular momentum. In the next video, I'll go over rotational kinetic energy, which is the last concept in this topic.